Hello, this topic is the one more application of chi-square distribution to check the goodness of fit test. When say goodness of fit test means we want to check what distribution the data follows. If the data is following uniform distribution, then we want to confirm whether the really uniform distribution is followed or not. If the claim is made that the data follows a particular specified distribution, then we want to like to confirm with chi-square test that that particular distribution is followed. Let's see, the hypothesis here is that the population follows a multinomial distribution with a specified probabilities for each of the k categories. And the alternate hypothesis will be opposite of that. The population does not follow a multinomial distribution with specified probabilities for each of the k categories. Let's see one problem to understand the application of goodness of fit test. Before that, let me explain you the procedure. The procedure is that select a random sample and record the observation, that is observed frequency Fi, for each of the k categories. Next, if we assume that null hypothesis is true, that is the data follow a specified distribution, then according to the specified distribution we'll have a probabilities for each of the category. So multiply that probabilities with the sample size, and with that you will get expected frequencies. That's we are going to denote as EI. So now with this we have a observed frequency Fi and we have a expected frequency, that's EI. Once these two numbers are available, we can find out the difference Fi minus EI, square of that to get rid of the negative sign, divide by EI to standardize it so that it can be compared with the available table. The test statistics has to be compared with the critical value of chi-square, which is found out by having a degree of freedom k minus 1 minus c. The k is number of category, and in case if the data follows a particular distribution set, let's say normal distribution or a binomial or a Poisson, then c has to be selected accordingly. However, here the one thing is to be noted that each expected frequencies should be phi or more. Let's take one example. For a particular survey of a distribution, the expected distribution is that excellent category will have a 8% of the respondent, pretty good will have a 47%, only fair 34%, and poor 11%. This is a national average. Let's say, suppose a particular store manager wants to confirm whether the result of this his consumer survey applies to consumer of its supermarket in her city. The result of her survey is that in their case they got 21 respondents saying excellent, 109 saying pretty good, 62 saying only fair, and 15 saying poor. So we want to determine whether the observed frequency of the response, that is the data from the survey, that is this part, is same as the frequency that would be expected on the basis of the national survey, that is this percentage. So we want to confirm whether this national percentage, let me show a pointer here. So the national percentage, this distribution is followed in this case or not. So as a first step we have to, let's say, frame a hypothesis. So my hypothesis is that the observed distribution is same as the expected distribution, and alternate is opposite of that. And since we have a formula, FO minus FE upon FE, the FO is the observed frequency, FE is the expected frequency. Now how we are going to compute this two? The observed frequency is this data, and my expected frequency will come from this. So I have to add up this, which will give me my sample size. That sample size multiplied by 0.08 will give me the expected frequency for excellent category. Similarly, the sample size multiplied by 0.47 will give me the expected frequency for pretty good. Then sample size multiplied by 0.34 will give me the expected frequency for only fair, and rest are the poor. So with this I'll have a FO and FE both. So let's see the FO values, FE value, that's expected frequency. So we have excellent 16.56, pretty good around 97 point something, only fair around 70, poor 22, and my total sample size 207. Now with this FO and FE I'm comparing, and the difference I find out 21 minus 16.56 is 1.19, 21 minus 16.56, that difference square divided by 16.56, I'll get 1.19, and so on and so forth. The summation of that is 6.25. This is my computed chi-square. If the data follows the expected distribution, then this difference will be smaller. Ideally it should be 0, but it can be slightly more than 0. But if it is significantly more, then we are going to reject the null hypothesis, which says that the data follows a specified distribution. In our case, the difference expressed in terms of chi-square is 6.25. For this case, where we have a level of significance as 5%, and since there are 4 categories, and we are not using any of the parameter of the given distribution, so the probability is directly given. So it's going to be a k equal to 4, c equal to 0. So 4 minus 1 minus 0 will give you 3. So we have a 3 degree of freedom, 0.05 as my level of significance. The chi-square value from the table will be 7.8147. We observe that the computed value is less than the critical value. Hence, we will not reject the null hypothesis and will say yes, the data collected by a store manager do follow a national the probabilities given by the national survey. Let's see one more question where we are saying, does the monthly figure for milk sales are uniformly distributed? So we have a 12 months data from January to December. Now once we say uniformly distributed, that means each month probability will be 1 by 12, right, because it's 12 months. So what I'm going to do, 1 by 12 multiplied by 8447 will give me the expected frequency for January. Similarly, February, March, April, May, June, July, August, for all the months same. So we will compare the observed frequency which is given in this slide and the expected frequency we'll get from this sample size into 1 by 12. We'll compare as given in the earlier problem, and we'll find out the computed chi-square value, compare that with the critical value. Here again take alpha is equal to 0.05. Since we have a 12 months, so my k is equal to 12, and degree of freedom for chi-square critical value will be 11. So I'd request you to pause the video for a while and go ahead and solve this problem. The next application is, many times we make an assumption that a data follow a normal distribution. So how to confirm it? So let's say we have this data, sample of 30 observation. Let's check whether this data is following normal distribution or not. So first task will be to find out the mean of this data and the standard deviation of this data. So my null hypothesis is that this data follow a normal distribution with a mean equal to 71 and standard deviation is equal to 18.54. That's my null hypothesis. Alternate hypothesis is that it doesn't follow normal distribution. Now, since we have a 30 observation and the technique requires that expected frequency should have at least 5 observation. So in earlier 2 problems the category were given. Now here the number of category we have to decide. So what we will do here is that we will divide all the full normal distribution into categories which are having equal number of observations in case of expected frequency, and it has to be 5 or more than 5. So my category frequency for the total 30 observation should be 5 each category. So 30 divided by 5 So there has to be 6 categories. Now what will be the limiting values for those categories? Obviously minus infinity to a particular value, that will be my first category. Then first particular value to the next particular value, second category. That particular value to the 71 is the third category. 71 to the next particular value is the fourth category, and so on and so forth. So what I'm going to do, I'll divide the whole distribution into a 6 part, each part having an equal probability. That's 1 by 6. So if I multiply 1 by 6 by 30, I'll get 5, 5, 5 each. Now since I know the probability for this particular area is 0.167, I can look at the normal distribution table, can find out the z value. Since I know the z, I know the mean, that's 71, I know the standard deviation, I can find out x value, that is in this case going to be 53.02. Similarly, since I know the total area to the left of this line is 2 by 6, so that's my probability. I'll go to the normal distribution table, find out the z value. With that z value, find out the x value. In this case it comes out to be a 63. 71 is anyway middle number, and the mirror image of this will be here. That's how I got a 6 range for expected frequency. Now I'm going to say it from my 30 observation, how many observations are less than 53.02. So observed frequency is 6, the expected was 5. Similarly, how many observations are between 53.02 and 63.03? The observed numbers is 3. That means there are 3 observations which is lying between 53.02 and 63.03, and the expected number is 5, so on and so forth. So this way I have a observed frequency, that's a Fi, and expected frequency, that's a Ei. I can find out the difference. The square of the difference, express them as a ratio of difference square divided by expected frequency. We will get the computed value for chi-square. The computed chi-square value in this case is 1.6, and the chi-square value from the table is 7.815. We have assumed alpha is equal to 0.05, and the parameter, number of parameters used to find out the expected frequency is 2, because we have used mean and standard deviation both. So that's why P is 2. So 6 category minus P, that's 2 parameter, minus 1, so 3 degree of freedom. So we can see here computed value is much lower than the critical value, so we conclude that the data do follow a normal distribution. That's all, friends, for this application of chi-square test for goodness of fit test.